So you'll notice these same rules are making an appearance that were in the last video. Again, I can't overemphasize that these are vital to your success on the next test and all the homeworks. Understanding these rules, being able to use them. So we will use a few today, and that's kind of why they're up here now. I've also numbered them, so that way they I can refer to them by their number. Notice that this one, x to the m plus x to the n, does not have a number. It's because he's really not a rule. This is just a reminder that if I have an x squared term and an x cubed term, I cannot combine them. They're not like terms. So that's up here, but I wouldn't necessarily call it a rule because it doesn't really say anything and it doesn't help us simplify. Okay? So exponential functions, which were in the last video, looked like the following, right? That was the growth, and then we had a separate one that maybe we called decay. And no matter how I might shift this, right? Maybe it gets shifted up because I add something at the very end of the function. Maybe it goes left because I add something near the x. Remember all your translation rules. No matter how I shift these, they are still one-to-one. They pass that horizontal line test that was part of the inverse functions video. So every horizontal line will only hit the function in at most 1 point, okay? So because they're one-to-one, we have the following fact that we can use. All right, keeping it very generic. If I keep it generic and use letters, that means I can apply this fact for a problem that later will have numbers. But if I see something with the same base, so this a is called the base, and then up here, the superscript is called the exponent. So if I have the exact same base, but possibly different exponents, the exponents are actually going to equal one another. That's because of the definition of one-to-one, right? Every output has exactly one input. So if I'm saying, oh, the outputs are the same, then it must be that the inputs are also the same, okay? So if this equal sign works, this equal sign also works. And this is actually if and only if you've taken logic, maybe you've seen this symbol. What it just means is if you see something on the left, you can infer the thing on the right is also correct. If you see something on the right, you can conclude that the thing on the left is also correct, okay? So you'll need one of these, and then you know the other one's also true. So this is helpful when we solve equations with exponents. So I'm going to write one up here. 3 is a base with an exponent 5x, which is then multiplied by a third, but a third is a base that's raised to the exponent 8. That's the left-hand side. Now the right-hand side, there's the number 9, and then a power, or an exponent of x plus 2. And you know, it's a solve. That means I have to figure out, okay, what is x in this situation? All right. So my goal is to exploit the thing above. And I can only do that. Don't start doing crazy illegal things. Don't start trying to multiply 3 times a third here. You cannot do that and respect order of operations. Exponents happen before multiplication. Remember PEMDAS, or please excuse my dear Aunt Sally, or whatever acronym maybe you learned in a previous course. I cannot multiply these together because there's an exponent in the way. So right now, I really can't combine them unless I start using my exponent rules. But let's go over that goal. My goal is to have the same base appear once on both sides of the equal sign. Okay, so same base appearing once. So that way it's like a number to an exponent, and the same number, same base, appearing exactly once on the other side. Once I have that, then I can simplify the problem. Okay, so that's the goal. If you're not quite sure where we're headed, I'll point out when we've reached our goal, so that way you can kind of make sense of what those words mean. Okay? All right, so what can I do? Again, I cannot multiply 3 times a third. Don't do that. Illegal. PEMDAS, please excuse my dear Aunt Sally, tells you no, can't do that. Okay? So this 1/3, okay, well, that comes up right here, right? 1 over x to a power. I can actually rewrite that with rule 5. Rule 5 says I can rewrite that as 3 to the negative 8 exponent. That's what I'm going to do first. So not changing that at all, but I can change the 1/3. Again, 1 over 3 to the 8th I can rewrite as 3 to the negative 8. That's what I'm doing. I'm executing rule 5. On the right-hand side, okay, if I remind myself of my goal is to have the same base everywhere. We already have bases of 3 on the left, so it would be nice if I could also get a base of 3 on the right. Again, I cannot multiply the 3 times the 3. There's an exponent in the way. I cannot call that 9. Don't do that. Illegal. Not a proper rule. But that 9, I know is 3 squared. 9 is 3 squared. That's nothing new. But that 9, or 3 squared, is still raised to the x plus 2 power. Okay? So I just rewrote 9. Wouldn't call that a rule. I would just call it a fact. 9 is 3 squared. On the left-hand side, okay, I'm in the situation like rule 1. 3 is my x, and my m is 5x, and my n is negative 8. So I can combine those exponents with addition. So rule 1 tells me the right-hand side is 3 raised to the power 5x minus 8. On the right-hand side, that is reminiscent of rule 3. I have a base, and then I have an exponent raised to another exponent. So I can simplify this with multiplication. So I'm going to be multiplying 2 times the quantity x plus 2. Using rule 3, the base does not change. So I'll have a 2x plus 4. I am multiplying to both terms. I'm distributing. This says multiply. I need to multiply to all parts. We reached our goal. Same base, 3 and 3. Appearing once on the left, appearing once on the right. Once I have that, here's how the problem simplifies. It's exactly this rule. Same base, different exponents. I can now set the exponents equal. So because of our rule, 5x minus 8 is equal to 2x plus 4. And now I have what I would call like an algebra 1 problem. Okay, I just have to solve for x. So maybe I'll move the 2x over to the other side. With subtraction, now it's a 3x. Simultaneously, I'll add the 8 to the 4. Oops. I said 4, but that's not the sum. 8 and 4 is 12. And then divide both sides by 3. That is how we solve, okay? You will have a chance to practice this, but if you are not able to come up with these rules on your own, you know where you have to go. I think it's page 17 and 23 in the text. Set up note cards, quiz yourself, look over those prerequisite rules to get a better understanding of these fundamental things we're going to keep using, okay? All right, we're going to transition now to the next section. So next section I'm calling 4.3, the natural exponential. So we're still talking about exponents. So I'll leave those rules up there. They might be useful. Starts on page 274. Okay. To get us started, the previous video talked about exponential functions, and at the end we talked about money, right? Compound interest. Well, with money, right, if you're the investor, more compounding terms, which was your n in the equation, meant more, or means a larger accrued amount, which in the equation we called A, okay? So if you are investing your money, you want to look for accounts that are compounding daily, not compounding monthly. We want more terms to compound, okay? If we're investing. Now, if you're taking out a loan, you want the reverse because you don't want to owe. You want like compounded hardly at all, maybe semi-annually, twice. Not compounded daily because then you owe more interest, okay? So this brings us to, what if, instead of compounded daily, or instead of compounded monthly or weekly, what if we compounded continuously. Okay, what that means is every moment of every second, of every minute, of every hour, of every day, of every week, of every month in the year. We're always compounding. We're always racking up that interest. Then the number of terms is actually infinite, right? If it's every moment of every second, we're always compounding. And n, I don't say n equals infinity. Can't plug in infinity. It's not a number. It's not a button on your calculator. I'm saying n is approaching infinity. We're getting as big as we possibly can, okay? So in that situation, let's kind of explore what happens. So this is our compound interest formula from the previous video. Now I want to talk about what's going to happen as n gets really, really big. But I'm going to do some manipulation of this function, okay? You will not be expected to do this manipulation or develop this formula again, but I do want you to see it in context, to see where it comes from. And I'll talk about the steps I'm executing here. Instead of having r over n, what I'm going to do is take sort of the reciprocal of that. I'm going to say, okay, that is the same as 1 over n over r. Here's what that means. If I have 1 divided by a half, well, 1 divided by half, that's the reciprocal of a half. The reciprocal of a half is 2. All right, if you don't believe that, plug it into a calculator. If you have 1, you divide it into half parts, you have 2 parts. I'm using that same idea here. That 1 over a fraction is just the reciprocal of that fraction. Okay, so I still have equality. I'm going to do a little bit more as well, okay? I'm going to take the exponent, I'm going to simultaneously divide by r. So there's division by r, but if I want to maintain equality, I have to undo that with multiplying by r. Okay, so I'm simultaneously dividing and multiplying by r. Okay, everything in here, okay, that is everything inside those square brackets right now. We can actually pinpoint that to a number, okay? Looks crazy, looks wild, but remember, n was big. So if n is big, dividing by our interest rate isn't going to change n being infinitely big, right? If n is infinite and I divide it by 5, I'm still infinite, okay? So everything inside those parentheses or square brackets, it's about that number right there, okay? I would take a moment, I would pause the video, and I'd actually try to plug something in, right? Plug it into your calculator. What is 1 plus 1 over 10,000? All raised to the 10,000 power. You should get something about this. This is a very important number in math. This is the number e. Just like pi, it's one of those non-repeating, non-terminating decimals that becomes a very powerful tool, okay? So you should have an E button on a scientific calculator, or even if you type it into Google, Google will do the calculations as well, and it will know that E is approximately this decimal. So that's going to simplify our formula. P is still there. Everything inside those brackets is the number E, and on the very outside of the brackets, I still have an exponent of RT. Okay, so we call this PERT formula. Maybe you've seen this formula before, or maybe you will see it in like a business class or something like that. But PERT formula is what we use. So this E, or this formula, is used to model growth or decay of quantities growth or decay, let me rephrase, that occur at a rate proportional to size. Okay, that's a mouthful right there, but it's there to distinguish it from linear growth or linear decay, right? Remember, like the baby that just gained 10 pounds every year. Didn't matter what year it was in, it was always 10 pounds heavier, 10 pounds heavier. That's probably not realistic because growth is probably going to occur at a rate proportional to your current size. Okay, right? If you have a lot of money, you're probably going to make a lot of money. If you have very little money, you're going to make very little money, right? That's how interest rates work. It's all about being proportional to their current size. More money begets more money. Less money makes less money, okay? So keeping that in mind, we're no longer growing things linearly. But we do want to look at an example of some kind of situation that's like this. Okay, so that situation says we have a radioactive isotope. Decays at a rate of 0.79% per year. How much of a 100-gram sample remains after 1 year? No, I'm sorry, remains after 88 years. Okay, so let's kind of break down what's being asked of us here and how I know which formula I might need to use. And when you're presenting your videos, you also need to start breaking down formulas. If you just throw a formula up there, it's not very helpful to the class unless you explain the context. Where did it come from? Where are the parts? How do I know what goes where? Okay, so because I'm decaying at a rate of a percentage per year, I know I'm not going to be aligned. This doesn't say I lose 10 grams every year. The more of this isotope I have, the more I lose. The less of it I have, the smaller the percentage I lose, okay? Because it's a percent. The more I have, the more I lose. The less I have, the less I lose, okay? So it's proportional to size. So I'm going to be using this PERT formula, okay? All right, what else can I diagnose? How much of a 100-gram sample? Okay, this is my original amount. We call that P, sort of like the principal. Remains after 88 years. This is the easy part to diagnose. That's T, time. The fact that we are decaying at a percentage, okay, those two pieces together indicate that R is negative. I'm not growing this isotope, I'm shrinking it. It's a negative rate. Change percents to decimals, so it's actually negative 0.0079, changing a percent to a decimal. And then what is this asking me for? Well, it's asking me how much remains. How much is at the end? It wants to know A. So I'm going to plug in everything we've got so far. 100e to the negative 0.0079 times 88. Okay. Order of operations again, I kind of have to do the exponent part first. So I would multiply these together. Then I would have e raised to that power. Find a calculator that has e, or like I mentioned before, you can literally type this expression into Google as long as you get your parentheses right. So let me show you what this would look like with proper parentheses as well, just so you don't get calculator errors messing you up. So you do e, and then probably the caret symbol, and then open up parentheses because both of these are up in the exponent. Okay, so something like that to plug in the calculator. Okay, again, putting parentheses around both of those terms because they're both in the exponent, not just one of them, and the caret raises everything to the exponents. Okay, what you should get is 49.9. If you have not attempted this on your own, do it now. Make sure you understand the syntax of your calculator, okay? If you don't understand it now, you can contact me. I'll try to help you through it, or just send me a picture of the calculator. It's maybe one I've seen before. But if you cannot get this number on your own, it's going to be very hard to get the WebAssign answers right on your own as well, okay? So this is an amount in grams. So this is actually a pretty special number here. We started with 100, and we ended up with about 50 left. So in this situation, right, this is the final answer to the question. But in this situation, I would say that 88 years is the half-life of the isotope. Half-life meaning the amount of time it takes for the entire isotope to be cut in half. Okay, so if pretend this was 100 grams of the isotope, 88 years later, this is how much remains. So 88 is the half-life, how long it takes for half of it to remain. Okay, so as a follow-up, I could ask, when does 25 grams remain? And I can solve this without doing any algebra. Okay, half of 100 is 50. As I'm saying, this is about 50. Half of 50 is 25. So if I have this half-life and then it goes in half again, we're calling that about 25 grams. Okay, so we had the first 88 years to get us down to 50 grams. Another 88 years would take us down to 28 grams. So 88 plus 88 is equal to 176. So 176 years from the beginning. Okay, so 88 years to get down to 50, and then another 88 to get down to the 25. Okay, that's nice about half-life. You don't have to do a lot of algebra as long as all your numbers are halves of each other. Okay, all right, good luck.